it just gives basically an expression for the lift force. See, this expression for lift force is something which may be quite interesting, because what is happening here, you have a circular cylinder, you have a uniform flow like this, you make the cylinder rotate like this, okay. Once you make the cylinder rotate like this, there is a force which is exerted on the cylinder towards the top. Just in place of a cylinder, if you replace a sphere, qualitatively it does not change much. So think of a case, you have a ball which you are rotating with this type of axis and it just goes upwards, that is the top spin of a ball. So this effect is known as magnus effect in fluid dynamics. So with this background of potential flows, we have come to a stage when we may appreciate that what is the consequence of the pressure distribution around the body, at least, and till the boundary layer gets separated, the consequence of the pressure distribution is something which is consequential for flows of past bodies of all shapes except flat plate, where the pressure gradient is not important. Now let us look into some bodies of other shapes. We will not calculate similar expressions because we have just seen a strategy of doing this, and in fact there are many interesting transformations by which you may convert from one shape to the other. So for example, you have a transformation which may transform, a geometric transformation which may transform a very thin flat plate or a very thin foil like this into the shape of a circle. So there are similar, so this transformation, I mean there are certain special transformations which do that, and in general these types of transformations are known as conformal mapping or conformal transformations. What they do basically, if you have a set of lines in the original configuration and a set of lines in the transformed configuration, it retains the angle between that two preserved in the original and in the transformed coordinate system. But we will not go into that transformation. We have in our one of our homework problems, we will be giving you a problem to solve related to this transformation, but I mean that you may do by considering all the basic theoretical backgrounds that we have already developed. Now what we will try to see next is that keeping in mind that shapes of different bodies of different shapes may be generated by suitable transformations from a simple shape to maybe a complex shape and so on. Generically we are in a position that if we know how to generate potential flows past simple shaped bodies, we may generate such flows even for bodies of complicated shapes. But what are the important consequences? To do that, we will study the flow past two important shapes of bodies. One is like a aerofoil section and another is flow past a circular cylinder in somewhat more details than what we have done till now. So when we consider the real flow, you have to keep in mind it is not the potential flow, you have the boundary layer effect plus the effect due to the pressure distribution that we are seeing. So the pressure distribution is there, which is imposed from the free stream into the boundary layer. So that you can calculate from the potential flow. More or less it will not be very inaccurate till there is boundary layer separation, but in reality there is boundary layer separation. Therefore in reality whatever the pressure distribution is predicted by the potential flow does not work. It works approximately well till the point of separation or very close to the point of separation, but not far away from that. So first of all we will consider the case of say flow past aerofoil sections. We will just learn some important terminologies. So flow past aerofoil sections, so let us first make a sketch of the section that we are considering. Just consider it like a section of like a aircraft wing, Okay. So now there are certain important dimensions which are given to it. One is the dimension of this transverse one, and another is this one which is called the chord of the aerofoil. This is called the chord. If you calculate the lift and the drag force and the corresponding coefficient, say you calculate the lift coefficient. So what is that? That is the lift force divided by half rho u infinity square into the reference area. We have seen that for flow past bodies of like shapes of cylinder or sphere like that, the reference area is what? The reference area is like the projected area. In this case, where the bodies are of much slender shape and slim shape, so to say, the reference area is called as a planform area. Reference area is different by engineering convention for different things, like if you have a ship in water, then it is the submerged area that is considered as a reference area. So it depends on what is the object that you are looking about. So reference area, the planform area, that is the area that you view from the top, that is B into C. Okay. So that is the reference area, and the second thing is that what is important is to know that what is the, so if you just draw the sketch of a section, so this is the chord of the aerofoil. Now what is the angle made by the incoming flow with this one? So let us say the incoming u infinity is like this. So the angle made by the u infinity with this chord, let us say alpha, this is known as angle of attack. This angle of attack is very, very important, because if the angle of attack is very small, then the original flow is almost aligned with the direction of the chord, and then the flow's boundary layer separation takes place almost at the trailing edge, I mean almost the entire flow is unseparated. But as you increase the angle more and more, you will see that beyond a critical value of the angle there will be very quick boundary layer separation, and because of that very quick boundary layer separation, the lift force will go down. So if you just draw the coefficient of lift versus the angle alpha, so it will increase, then it will come down, it will attain a maximum roughly at about say alpha equal to roughly 10 to 12 degree, let us say 12 degree as an example, and then it falls down, because then there is a large separated region. Because of the great mismatch between the direction of the flow and the direction of the chord, the flow separation takes place quite quickly, very early, and this kind of situation, that is at this angle, it is called as that the aircraft or that aerofoil is stalled. So this is known as a stall. So one of the important objectives is to generate a lift force. So you may increase the value of alpha to generate a greater lift force if you want to go to a greater elevation. So you can see that if the aircraft has to have a different elevation, say higher elevation, it should have its aerofoil wing section oriented in a particular fashion with the relative velocity of the wind that is there outside, or the relative velocity between the outer ambient and the aircraft. So that angle has to be adjusted properly to get the proper lift, but once it is in a particular height or a particular level, then you do not expect a net thrust or a net lift. That means the weight is balanced by the lift force and it is just in sort of equilibrium. Similarly the drag force is balanced by the thrust, so if it is in a sort of an equilibrium and moving. So these are some of the important things. Let us look into some animated descriptions of how fluid flow takes place past an aerofoil. So first let us, so we will see quickly that what are the impacts of different angles of attack.
So why the lift force is small when alpha is high?
So if you calculate the lift force, obviously that will come from the proper evaluation of the expression. So if you evaluate the proper lift force for flow past an aerofoil, you will see that it will depend or it will increase with the alpha so long as you do not have a large separated region. That is quite clear. So just think very physically, if there was no separation and a flow is like from the bottom, it would lift it very significantly. If it is horizontal and inclined with it, how can it lift it? So as you increase the inclination, you have a chance of lifting it more and more, but if you have boundary layer separation altogether, then that effect is lost. So let us look into the different cases of aerofoil flow. This is like a sort of a potential flow type of situation. So this is a simulated condition, of course. This is a flow visualization example. So see carefully, some dye is injected around the section and how the dye takes its turn. So these are like examples of streak lines in a steady flow, these are like streamlines. Okay, let us look into the next example. So now we will see the effect of different angles of attack. So this is aerofoil section where you have 0 angle of attack. Now let us say 15-degree angle of attack. So with the increase of the angle of attack, you see what is happening. You see a flow separation that is taking place quite quickly. So whatever is that circulating region, that is a region of low pressure beyond the separation. Look for the angles of higher and higher orientations, you see that the effect of the separation becomes more and more severe. Okay. So these are just, this is a 60-degree angle of attack. So you can see that as you increase the angle of attack, the severity of the consequence of separation becomes more and more prominent. So that is one of the important things that we learn from this. Now if we go on to study the flow past different shaped bodies, till now in the boundary layer theory we have considered cases with high Reynolds number. The reason is quite obvious, that if you have high Reynolds number, then only the boundary layer theory you may apply, but there may be interesting cases when the flow is very slow, or the relative motion between the fluid and the solid is very slow, that is also flow past the body. And therefore let us quickly see what is the consequence of very low Reynolds number flows. Very low Reynolds number flows. Okay. So when we say very low Reynolds number flows, it of course depends on the length scale what we are talking about to describe the Reynolds number, but let us say much less than 1, that type of Reynolds number we are talking about. So such flows are called as creeping flows, as if there is an object which is creeping or moving at a very slow pace relative to the fluid. So when you have such a situation, think of the Navier-Stokes equation. In the Navier-Stokes equation, the left hand side is a representative of the inertia forces, right hand side the viscous term is a representative of the viscous force, and then you have a pressure gradient, force due to pressure gradient. So if the Reynolds number is very small, then obviously the inertia effects you may neglect. Now there will definitely be some error, because there will always be some inertia effect may be present, but if the flow is of very low Reynolds number, that effect is not predominant. So then the Navier-Stokes equation will take of the form 0 is equal to minus gradient of P plus mu Now we will, what we will do is we will proceed further with the curl of both sides. So to do that we will keep in mind that if you want to evaluate for example this curl of this one, that is del cross V. So this identity we have used earlier also for developing some other theory. So now if you have a situation where this it is an incompressible flow as an example, so this will be 0 if it is incompressible flow, and the curl of the velocity is what? It is the vorticity vector. So you can write this equation as 0 is equal to minus gradient of P minus mu into curl of the vorticity vector, right. We are replacing this del square V by this one. Now let us take a curl of both sides. So 0 is equal to okay. Clearly what is this? Curl of gradient of a scalar is 0. So vector identity this is 0, and this again we may write in the form of this identity. So we will write okay. Now what is this one? The vorticity is curl of the velocity. Divergence of a curl of this is 0, right. So this is 0, and therefore you come up with the final very simplified form, the Laplacian of the vorticity is 0. Okay. Now starting from this form, so one can start with a velocity or a stream function, evaluate the vorticity in as a function of that, so get a governing differential equation which does not have pressure. So this in a way what it has achieved, it has just eliminated the pressure. So from this it is possible to get the velocity field. So once you get the velocity field, it is possible to evaluate the drag forces, and for a very low Reynolds number flow it is you will have the shear effect very important. So you have the shear force, you have also the force due to pressure, and then you may use that to calculate the net drag force. And see, for very low Reynolds number flow you do not have boundary layer theory valid, because if you call something as boundary layer, that is extended till infinity, that is the viscous effects propagate far and far away from the body. So there is nothing called such a, of course technically we may say that still it is a boundary layer with an infinite thickness, but fundamentally the boundary layer theory is not valid, because it is valid only if delta by L is very small, which, so for such cases you do not have the boundary layer theory valid. So if you take an example of flow past a sphere, if you go through this calculation you will find out that the drag force is 6 pi mu into u infinity into r, where r is the radius of the sphere, provided that the Reynolds number is much less than 1. This is known as Stokes law. So in one of the assignments that we have given you, we have asked you to prove this by solving the Navier-Stokes equation and its through this vorticity form. That is given in one of our assignments if you evaluate it. So it will give you a practice of using the spherical polar coordinate system for solving the Navier-Stokes equation. Now if you want to calculate the drag coefficient, the CD is the drag force divided by half rho u infinity square into the reference area. The reference area is the projected area. So what is the projected area of a sphere? Pi r square, right. So what will be the expression for CD? 6 pi mu u infinity into r divided by half rho u infinity square into pi r square. So, this will become 24 by rho u infinity into 2r by mu. Why we have used 2r? Because the diameter or the 2r is usually considered as the reference length scale for the Reynolds number. So, this is 24 by Reynolds number based on the length scale of the diameter of the sphere. So, low Reynolds number flows are the other extremes of the high Reynolds number flows, where you have certain very interesting effects, and in reality the combination of low and high Reynolds number flows are important. That is, we may cover a wide range starting from very low Reynolds number and we go further and further to very high Reynolds number. In our next lecture we will see a lot of video demonstrations on how the flow past a body, say of a circular cylinder shape, will change as you change the Reynolds number from a low value to a gradually very high value, and whatever we get inference from that we will look into the second set of the demonstrations, where we will see the dynamics of sports balls. That is how you may control the movement of the sports balls by utilizing the basic aerodynamics that we have learned. So, that we will do in the next lecture. Thank you.